At the end of the last part of this video, I asked you this question. This is a question that we are often asking ourselves in the middle of labs, in the middle of working on assignment problems, in real life, thinking about, say, collisions between cars, and so it's important that you learn to think about these sorts of situations. So remember that the definition of isolated is that there are no external interactions. Notice that choices A and B have nothing whatsoever to do with whether there are external interactions, and so they must not have anything to do with whether the system is isolated, and so that can't be right. Now, C is tempting because it's the only answer that actually talks about external interactions. However, I'll note that what we've been seeing is that any time there are no external interactions, it is always true that the system's total momentum is constant. In other words, one implies the other. And so we can see that the total system momentum, this yellow curve here, is roughly constant. And so approximately the system's momentum is constant, and that tells us that there must not be any external interactions. A note on this: sometimes it's easier to think about whether there should be external interactions, and perhaps it's clear that there must be, or it's clear that there must not be. Other times, and I would say this is one of those times, it's not really clear from the situation whether there would be strong external interactions. But we can always measure inertias and velocities relatively easily. And so usually our best experimental evidence for whether a system is isolated or not is whether its momentum changes. Throughout this unit, I've largely been sticking to cases in one dimension, but let's now move on to 2 dimensions, and there's actually not much to it. We can write conservation of momentum as a vector equation. I'm going to say let's stick to the case of an isolated system where there's no impulse. And so this can be expanded out, say, for a 2-object system like this, to look like this, where we have the sum of the initial momentum equaling the sum of the final momentums. So, as we've done before, let's now introduce axes and write this out in full in terms of components. And I'll warn you before I do this that this is going to be an intimidatingly large-looking equation. Don't panic. The whole point of what I'm showing you is that I want you to see how to make it less intimidatingly large. So, just writing out each velocity in terms of its components, it looks like this, and that looks pretty awful. But remember, we can take a vector equation and split it into a pair of scalar equations. We've seen that, for example, with the position as a function of time for constant velocity. So we can do exactly the same thing with our conservation of momentum equation here. We can take all the x components and pull them out into their own equation, and we can take all the y components and pull them out into their own equation. And now we have 2 much more manageable equations, which we can solve much more easily and which aren't nearly so scary to look at. Once you've written out the conservation of momentum equation, or if you want to think of it that way, the 2-component equations for conservation of momentum, you're largely done doing the physics, and it's all math from here, and not particularly hard math usually. Let's look at a common situation where, say, you know the initial velocities and you want the final velocities of both objects. Then here are your conservation of momentum equations, which we just saw before. And I'll note that before you do anything, you should probably count unknowns. Well, look, we have 4 unknowns because each velocity has 2 unknown components. And so there are 4 unknowns, but only 2 equations. And there's actually nothing more we can do. We can't solve this without more information because we don't have enough equations to deal with those unknowns. Another common situation, though, would be a situation where the 2 objects stick together and move with a common final velocity. Now your conservation of momentum equations are going to look like this. You only have two unknowns and two equations, and so this would be perfectly solvable. Actually solving two-dimensional collisions can get a little heavy on algebra sometimes. I'm not going to do any examples in this video because it just takes too long. However, I will provide a supplementary video where I'll solve one one-dimensional collision and another one that's in 2 dimensions.